Welcome back. Problem 5.101. This problem is taken from chapter number 5, Analysis and Design of Beam for Bending, and book name is Mechanics of Material by Beer and Johnston, 6th edition. And the topic is Singularity Function or Macaulay's method. So statement of the problem is using singularity function, write the equation defining the shear and bending moment for the beam and loading shown. And in part B, use the equation obtained for bending moment M to determine the bending moment at point E. And check your answer by drawing the free body diagram of the portion of the beam to the right of E. So you can see this is overhanging beam having pin support at point A and a roller support at point C. And there is a distributed load, uniformly distributed load from B to D having magnitude W naught. So the total length of the beam is 4 times A. Clear? So what we have to find is that using singularity function, we will write its shear and bending moment equation, and then bending moment equation, we will find the bending moment at point E. So for x is equal to 3a, we will find the bending moment. And then at the end, drawing the free body diagram of portion beam right to the E. So this is the right side of the point E. So we will find this bending moment by using the section at the right side. So let's start with the solution. So first step is that if you remove this pin support at point A, so you will be having reaction force, let this is A, and if you remove this roller support, so you will be having reaction C. So we'll find this A and C by using equation of equilibrium. And what if you convert this uniformly distributed load into point load, so it will be W times the length over which it acts, and the length, this is the length 3a. You can see this is 3a. So I will write it W into 3a, and that will act at a distance of a by 2 from this side. A by 2. Okay, this is the distance. Now we can apply the equation of equilibrium. So first equation of equilibrium is that sum of all moment about point C is equal to 0, taking the counterclockwise movement as positive. So about point C, the first movement is this A force and perpendicular distance is 2A, and it is producing clockwise movement. So I will take it as negative. So I will write A multiplied by 2A, and that is negative. The second moment that is produced about point C is this W naught into 3A, and perpendicular distance is A by 2. And this is also producing clockwise, so it is also negative. So I will write minus 3 W naught into A by 2 is equal to 0. The sum of all moment about point C is equal to 0. So I will write 2A into small a is equal to minus 3 W naught A square over 2. So what if I need A? So I will divide 2A on both sides. So minus 3 W naught A square, and it will become equal to 4A. So we will get minus 3 W naught A over 2. A over 4, sorry. 4. So what I get is A is equal to minus 3 W naught A over 4. This is the reaction force offered by pin support at A on this beam. Now we'll find this Cy by using another equation of equilibrium, that is sum of all moment about point A is equal to 0, and taking the counterclockwise moment as positive. So about point A, the first moment is this due to this force C, and perpendicular distance is 2A, and this is producing counterclockwise movement, so it is positive. So we can write C multiplied by 2A. The second moment is produced due to this W naught into 3A force, and now the perpendicular distance is 2A plus A by 2, which is equal to 5A by 2. Clear? So I will write, this is producing clockwise, so I will write 3 W naught into A into 5A divided by 2. Because you can see A plus A by 2, we take LCM, so 2A plus 2A plus A is equal to 5a divided by 2. So this total distance from this point till this point, this is 5a over 2. Okay. Now their sum of all moment about point A is equal to 0. So I need C. So 2AC is equal to 3 into 5 is 15. So I can write minus 15 plus 15 into W naught A square over 2. So it will give us from this we will get this C will be equal to 15 W naught A square over 4A, and that we will get C is equal to 15 W naught A square, sorry, A will cut and we will left with this one. So this is the reaction force offered by pin roller support at this beam. Now we will use this table in order to find the shear force and bending moment using singularity function. So here we have calculated A is minus 3 W naught A divided by 4 and C is equal to 15 W naught A over 4. Okay, so starting from the shear force diagram, so I will write V of X is equal to the first load starting from this left side hand side and moving toward right side. So first load is A, clear. So for point load, the figure is this, and for that shear force equation is this one. Since load is downward and it is at a distance of A, and here the load is upward and A is equal to 0. So we can write it as, for downward load it is minus P. So here I will write instead of P we have load A into X minus A is equal to 0. So it will be AX naught. Okay, the second load is, you can see, is uniformly distributed load and it is at a distance of A. So for uniformly distributed load, the shear force equation is this one, and this is downward, so it is minus W naught into, so I will write minus W naught into X minus A because it is at a distance of A from point A. And the third load is this C load. You can see this is a point load and it is upward, so we will again use this equation. So it will be plus C into, it is now acting at a distance of 2A from the A point. So I will write X minus 2A power 0. Okay, and this for distributed load, this power is 1. You can put the value of A, so A is equal to minus 3 W naught into A divided by 4, clear. And since X is equal to 0 at A, so 0 power 0 is 1. And minus W naught is same W naught into X minus A power 1 plus C, and C value is 15 W naught A divided by 4 into X minus 2A power 0. So this is your shear force equation. Now we'll find the bending moment equation, and for that we will again start from point A. So you can see this is point A having point load. So for point load, the bending moment equation is this one. For the downward load, here the load is upward. You can see the load is upward. So I will write plus A into X minus A, which is 0. So X minus 0 power 1. And for distributed load of W naught, it will be, you can see this is the equation for distributed load. So I can write, this is downward is negative, so I can write minus 1 over 2 W naught into X minus A, because this is acting at a distance of A from point A, power 2. And the last one is C, which is acting at a distance of 2A. So again for point load, I will go to this. So minus C, it will be plus C because the load is upward. So plus C into X minus A power 1. And you can see this C is at a distance of 2A. So correct it, This is 2a. Okay, now put the value of a. So a is minus 3 w naught a divided by 4 into x, because x minus 0, so x is 1. Clear. And the second one is this will become minus 1 over 2 w naught into x minus a power 2, and putting the value of c, which is 15 w naught a divided by 4 into x minus 2a power 1. And that is the required bending moment equation for the beam. Clear? Now we have solved our part first, which was using singularity function find the, this was part A. Using singularity function we have calculated or find out the shear force equation as well as bending moment equation. Now in part B we have been asked that use the equation obtained for M to determine the bending moment at point E. So you can see that this point E is at a distance of x is equal to 3a. So what we will do is that put x is equal to 3a in equation, for example, let this is equation number 1. So put x is equal to 3 in equation 1, so you will get moment is equal to uh, minus 3 w naught a into 3a, clear, divide by 4 minus 1 over 2 w naught, x will be replaced with 3a, so 3a minus a power 2 plus 15 w naught a over 4 into 3a minus 2a power 1. So we will get minus 9 w naught a square over 4, and from here we will get 2a square, so which will be 4a square, so 4 w naught a square divided by 2, and from here we will get 15 w naught, here we will get a, so a into a is a square over 4. This is moment m of x. And when you solve this it further, you can take the LCM, so 4 will be LCM, so it will be minus 9 w naught a square minus 4 w naught a square plus 15 w naught a square. So what we will get is moment will be equal to 9 minus 3 is minus 13 plus 15. So it will give you minus 2 w naught a square over 4. So it means that moment will be equal to minus 1 over 2 w naught into a square. This is the value of moment at point E. Now what we will do is that in the last portion we have been asked you check your answer by drawing the free body diagram of the portion of beam to the right. So what we will do is that we will cut the beam and at a distance of A from this side D, clear, and we will find the moment at this point E. So let me draw it. This is the beam, clear. This is your point D, this is your point E, where there is a distributed load acting downward, and this distance is given as A. And when you cut it, you will be having a shear force V and you will be having moment M. So we will find this moment E at point E. So how they will find this moment? So we will use the equation of equilibrium, that sum of all moment about point E is equal to 0, taking the counterclockwise moment as positive. So this was distributed load W naught. So when converted it to point load, it will be equal to W naught into the length over which it acts, so A. And it will act at a distance of A by 2 from either side. Clear? Now we'll apply equation of equilibrium, that sum of all forces about point E is equal to 0. So you can see one moment is clockwise, which is external reaction moment, that is clockwise, so it will be negative, and the second moment about point E is this, which is W naught into A into distance A by 2, and it is also clockwise, so it will be negative. So I can write minus W naught into A divided by 2 is equal to 0. So it means that moment about point E is equal to W naught A square over 2 minus. And again you can see it is minus 1 over 2 W naught A square. And you can compare it with the moment about point E that is obtained from moment equation from using singularity function. So it is minus 1 over 2 W naught into A square. You can check it, clear. And this is also minus 1 over 2 W naught A square. So this was all about this problem 5.101. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching.